So a couple more applications of utilizing the binomial theorem, one of which is to be able to find a specific coefficient for a given term of each of the expanded binomials. Where would you use that in real life? So if you were developing a model, a mathematical model, and you wanted to try to compare the terms, you could be able to find the error that exists between each of the different powers in an extrapolated polynomial. So that could be one example, or just to be able to verify that an algorithm is correct if you were to utilize an expansion. So to be able to just find the coefficient, all we have to do is we just have to identify a, b, and n, and then plug it right into the formula. So in this case, a is going to be 2x, b is going to be equal to 3y, and then n is going to be equal to 7. And this works really nicely because all the terms are linear. So if we want to figure out what that term is, we're going to say, oh, in this case, we also have to say what k is. K in this case is going to be 5 because that's going to be the exponent affixed to the second variable. And it's pretty clear that 7 minus 5 is going to give us the 2 for the x squared in our binomial formula. So if I was to throw this into the binomial formula, given all of these different parameters, then we can say that the term, or the coefficient, is going to be given by 7 combination 5, because remember that's n combination k. We're going to have 2x to the n minus k, so it would be 7 minus 5, because remember that's formula is a to the n minus k. And then we're going to have 3y to the k power, or in other words, b to the k power is the 5th power. Okay. And at this point, we're just going to compute. Okay. 7 combination 5, that should be 21, but I'm going to verify that using my calculator. So it's 21 for the combination. And then 2x squared is going to be 4x squared. And then finally, 3y to the 5th. 3 to the 5th should be 243. So 243, excuse me, y to the 5th. And we only care about the coefficients. So our answer in this case is going to be 21 times 4 times 243, or in this case, 23328. We could expand the entire binomial, and that would eventually lead us to that coefficient. However, maybe we're only interested in one specific coefficient because we look at a model and the model does something funny around that 5th power of x. A secondary example. Now this one's a little bit different because what you'll notice is that we have a nonlinear term. So really, when we think about the a to the 6th power in this one, it's really a cubed or a squared to the 3rd power. So this is going to be a squared to the 3rd power. And that's going to help us to be able to figure out what n minus k is. So if you ever have a quadratic or a cubic or something like that, you're going to have to restructure the way that you think about that first term or second term, etc. So we're going to define a. So a is going to be 3a squared. B in this case is negative 4b. Clearly n is 9. Right? And in this case k is going to be equal to 6. And it makes sense because to get to 3, that would have to be 9 minus 6. Right? So if we just left it as a to the 6th power, which we had initially, that wouldn't make sense. So again, for quadratics, it's helpful to write those quadratics as a quantity to whatever that power might be. All right. Now we're looking for the expanded polynomial a6, b6. So we're going to say that's going to be equal to 9 combination 6, 3a squared to the 9 minus 6, and then finally negative 4b to the 6th power. We're going to do some computation. So 9 combination 6 is going to be 84. And then we have 3a squared to the third power. So that's going to be 27a to the sixth. Although we really don't care about the a to the sixth. And then finally we have negative 4 to the sixth power, which is 4096 positive b to the sixth. So if we multiply that out, we're going to get a fairly large number. I end up with 9,289,728. Right. So one last example. What if both of the terms are now quadratic inside of the binomial? So we're going to have to think of x to the sixth as x squared cubed, and we're going to have to think of y to the fourth as y squared square. Right? So in this case, when we're defining a, b, n, and k, n is always pretty easy to define. All right? So in this case, a is 5x squared, b is the second term, which is negative y squared, n is always going to be the power to which the binomial is raised to. So in this case, it's 5. And then it makes sense that k is going to be 2. And the reason we can confirm that is because to get to that cubic, 5 minus 2 is going to be equal to 3 for that n minus k. So finally, we just throw it into the binomial formula. So we have n combination k, 5 combination 2, 5x squared to the n minus k, 5 minus 2 power, and then finally negative y squared to the k power, which is 2. At this point we compute. I'll verify this in a moment. 5 combination 2 is 10. We have 5 to the third power, which is 125. X cubed becomes x to the sixth power, and then negative y squared is just going to become a 1y squared. So ultimately we should wind up with 1250, because again we really don't care about the exponents or the variables. Right? And I do have to verify that 5 combination 2 is 10, which it is. All right. So when you're doing your practice problems, again, the first thing I would do is verify whether or not the terms inside of the binomial are linear, quadratic, cubic, etc. And if they are, then you're going to have to rewrite so that the powers inside of the parentheses match the powers inside of the expanded or the binomial that you're attempting to expand. And then from there, you can just implement the binomial theorem using your n combination k, a to the n minus k, b to the k power.